Okay, so let us continue our discussion on microvalves. We have been looking at thermoneumatic microvalve. So, in thermoneumatic microvalve, we basically we have a liquid present in a sealed volume, and we go for phase change. So, we supply heat so that the part of the liquid gets into vapor phase. So, there is an expansion of the volume, and the expansion of the volume basically actuates the microvalve. Okay. Let us now look at an example. So, this is the example, the valve that we have seen in case of the pneumatic microvalve example has a small actuation chamber and large gap for minimum pressure drop in the opening state, and the membrane is made up of silicon rubber, and the spring force is negligible. The initial actuating chamber height is 20 micron. Okay, so that is the actuating membrane height initially, as you can see here. The gap at the opening position is 500 micron. So, this is the gap. Okay. The way the water is filled and hermetically sealed at 1 bar 25 degree centigrade. So, inside here you will have water. Okay. In that 20 micron gap you would have water present at 1 bar and 25 degree centigrade, and while operating the chamber is heated up to 120 degree centigrade, and we are interested to determine the actuating pressure. Okay. The pressure that we have in this state, and we have the thermodynamic data for water at 120 degree centigrade. The specific volume of saturated liquid is given, and specific volume of saturated vapor is given, and the saturation pressure is also given, which is 1.986 bar. So, we are going to look at how we can find the actuating pressure. Okay. So, the first step we have to find the mass of the water inside the chamber. So, we have to find the mass of the water in the first step. So, the mass of water inside chamber can be found. So, m will be equal to V over V1. Okay. So, the volume will be 20 micron is the height, 20 into 10 to the minus 6 and into pi r square. Okay. R is 2 into 10 to the minus 3. So, 2 millimeter square. So, that is the volume of the chamber here. Okay, initial volume of the chamber divided by the specific volume, which is given 1.0029 into 10 to the power minus 3. So, that is water at 1 bar. So, this is for liquid water at 1 bar and 25 degree centigrade. So, the mass is going to be 250.6 into 10 to the power minus 9 kg. Now, in the actuating position, okay, in the actuating position, let us say the entire chamber is filled with liquid plus vapor. Okay. So, if that is the case, we can say that in the actuating state, the entire chamber is filled with water plus vapor. Okay. So, if that is the case, we can find the specific volume. So, the specific volume V2 is going to be V2 divided by m. So, the mass is not going to change, the volume has changed. So, the total volume, the total height here is 520 micron. So, this is 500 micron gap plus 20 micron. So, this will be 520 into 10 to the power minus 6 is the height into pi into 2 into 10 to the power minus 3 square divided by the mass, which is 250.6 into 10 to the minus 9. So, this will be 0.0261 meter cube per kg. Now, if you look at this specific volume is higher than the liquid specific volume, but less than the vapor specific volume. Okay. So, what we say is that this is a mixture, okay, and so the actuating pressure will be the saturation pressure, okay, the corresponding saturation pressure at this condition. Okay. So, the corresponding saturation pressure at 120 degrees C. So, the actuating pressure will be equal to the saturation pressure at 120 degrees C, and which is given by 1.986 bar. So, this is going to be the pressure at this condition. So, the inside pressure is going to be 1.986 bar. Okay. So, with that example, let us move on to thermomechanical valve. In thermomechanical valve, the principle is based on the difference in the thermal expansion coefficient between the actuating membrane and the base. Okay. And when there is a temperature change because of the coefficient of thermal expansion difference, the actuating membrane is going to expand. Okay. And the supply of heat to the membrane is going to actuate the membrane because of the expansion and contraction. Okay. So, let us look at thermomechanical actuators. So, let us look at thermomechanical actuators. Okay. So, here you can see the example, this is the inlet and this is the valve membrane. Okay. And on the valve membrane you will have some heaters present. Okay. So, the heater will be present on the valve, and when the heat pulse is applied, because of the difference between the thermal expansion coefficient of the membrane and the base, the membrane is going to expand. Okay. And let us say initially the membrane is contact with the valve seat here, this is the valve seat. So, the valve is closed. Now, if the heat pulse is applied to the heater, the valve is going to expand. So, the valve here there is going to be a gap between the membrane and the valve seat. So, the valve is opened. Okay. So, what happens in thermomechanical actuators is that there is a volume change due to thermal expansion. So, there is a volume change due to thermal expansion, and that force that develops because of thermal expansion is proportional to the temperature difference. Between the heater and ambient. Okay. So, that force is going to be proportional to gamma s, which is the expansion coefficient, into delta T. Okay. So, this is the expansion coefficient, and this is temperature difference. Okay. Now, typically we would have a membrane which is square or rectangular in cross section, and the membrane will be hinged at 4 sides. Okay. And so, okay. So, the membrane is going to be hinged on 4 sides, and the heaters will be mounted on these structures. Okay. So, initially this plate is going to be in contact with the valve inlet. So, the valve will be closed, and when the heat is supplied to these heaters, then there is a compressive stress that develops within these members, okay, 4 members, and at some point the compressive stress exceeds a critical value, and then the valve pops out. Okay. So, the valve is open. Okay. So, what happens is the compressive stress accumulated inside membrane up to critical value, okay, and this is going to be buckle and valve is open, and this buckling process happens instantly. Okay. So, the design of thermomechanical valve would involve design of the heater, its location, and also thermal isolation. So, these are important design parameters. Okay. And because the thermal conductivity of silicon is quite high, about 150 watt per meter Kelvin, the amount of energy that is required is also very high. Okay. So, the high conductivity of silicon so this requires several watts. Okay. Now, let us look at a bimetallic valve. So, this is the membrane itself, and we would have a bimetallic actuator mounted onto the membrane itself. So, this bimetallic actuators will have 2 different. So, this is the membrane, and here we have 2 metals. Okay. So, that is why it is called bimetallic actuator, and when the heat pulse is applied, because of the thermal expansion difference in the thermal expansion between the 2 different metals, the membrane will buckle to one side. Okay. So, in this case here the valve is in closed state when the membrane is in a buckling state, and when the heat pulse is taken out, the membrane will return to its original position and the valve can be open. Okay. So, this is the scenario we have. We would have 2 different metals bonded to each other. So, they could have different thickness, and when the heat is applied, because of the difference in the thermal expansion coefficient, in this case gamma 1 is less than gamma 2, there will the bimetal is going to deflect. So, there is going to be a maximum gap at the tip of the bimetal, and there will be an actuation force F, okay, which can produce equivalent deflection. Okay. So, we talk about bimetallic valves. So, the bimetallic valves is based on the difference in thermal expansion coefficient okay. So, this thermal expansion difference in thermal expansion coefficient between two metals, or it is also known as bimorph okay. And we would have a heater integrated onto bimorph. Here we would be the neglect temperature gradient across thickness, because we are talking about thickness of the order of micron, and we would have linear dependence between the heating power and the deflection okay. So, the deflection will be linearly dependent to the heating power okay. So, we can write the force would be proportional to the thermal expansion coefficient. So, the force that develops at the tip F will be proportional to gamma 1 minus gamma 2 into delta T okay. And the displacement at the tip, the displacement of the tip YL is going to be L square over 2R, where L is the length of the bimorph and R is the radius of curvature. Okay. So, the radius of curvature is given by this expression the radius of curvature R is given by B1 E1 T1 square whole square. So, B1 is the width of the bimetal 1, E1 is the Young's modulus of bimetal 1, T1 is the thickness of bimetal 1 plus B2 E2 T2 square. So, these are corresponding parameters for bimetal 2 plus 2 B1 B2 E1 E2 T1 T2 into 2 T1 square plus 3 T1 T2 plus 2 T2 square divided by 6 into gamma 2 minus gamma 1. So, this is the expansion coefficient difference between bimetal 2 and 1 into delta T beta 1 B1 B2 into E1 E2 T1 T2 into T1 plus T2 okay. So, that is the expression for the radius of curvature R. So, we can write the equivalent force F because of the difference between the thermal expansion coefficients, the bimetal is going to deflect okay, and there is the deflection is going to be maximum at the tip. Now, there could be an equivalent force F which can create the same amount of deflection at the tip if the temperature were constant okay. So, let us find that force F is the equivalent force which can buckle the bimetal like a cantilever. So that can be written as 3 into EI of the beam, the composite beam, into YL, deflection at y equal to L, divided by L cube. Okay. So that would be the equivalent force which can create the same deflection at the tip. Okay. And the flexural rigidity EI of the beam, which is called the flexural rigidity of the beam, can be found using this formula, which is B1 U1 T1 square whole square plus B2 E2 T2 square whole square plus 2 B1 B2 E1 E2 T1 T2 into 2 T1 square plus 3 T1 T2 plus 2 T2 square divided by 12 into T1 B1 E1 plus T2 B2 E2. Okay. So that is how we can find the flexural rigidity of the composite beam. So knowing that, we can find what is going to be the equivalent force. Okay. So here just to confirm, the B1 width of 1, T1 is thickness, so B is the width, T is the thickness, and E is the Young's modulus. Okay. Now if you assume that the two layers have same width, we can assume the two layers have same width, then the radius of curvature R can be T1 plus T2 by 6 into 3 into 1 plus T1 by T2 whole square plus 1 plus T1 E1 over T2 E2 into T1 over T2 square plus T2 E2 divided by T1 E1 divided by gamma 2 minus gamma 1 into delta T 1 plus T1 over T2 square. Okay. So that is the expression for the radius of the curvature if the two straps have same width. Okay. So in that case we can find the force F will be 3B over 4L into T1 plus T2 divided by 1 over T1 E1 plus 1 over T2 E2 into gamma 2 minus gamma 1 into delta T. Okay. So that is going to be the expression for the force. Okay. So with that let us consider an example. So this is the example we have a thermomechanical microvalve which has rigid square sheet of 500 micron 500 micron. Okay. So this is the rigid square sheet which has 500 micron area, and the valve seat is suspended on 4 flexors. Okay. So, these are 4 flexors 1, 2, 3 and 4. Okay. Each flexure is 500 micron long, each flexure is 500 micron long. So, each of these is 500 micron long and 200 micron wide. Okay. And the flexure is made of 10 micron silicon and 2 micron aluminum. So, it has 2 layers, as you can see here. The one layer is 2 micron, the bottom layer is 2 micron and the top layer is 10 micron. Okay. The silicon heater is integrated in the flexure. So, the heater is integrated onto the flexure itself. The aluminum layer is evaporated at 400 degree centigrade. Okay. So, the aluminum layer is at 400 degree centigrade. If a normally closed micro valve is to be designed at 25 degree C, then what is the maximum gap between the valve opening and the surface of the valve seat wafer? Okay. So, let us say it is initially it is evaporated at 400 degree C. Now, if we were to design the micro valve to be closed at 25 degree C, so it is getting the compressive stress, okay, because the temperature is going down. So, it is going to be compressed against the valve seat. Okay. So, we have to determine what is the maximum gap at which still the valve is going to be closed, okay, and the material properties are given. So, these are the material properties, the expansion coefficients gamma 1, gamma 2, okay, and E1, E2 of this aluminum and silicon. So, first we try to find the force at the tip of each flexure. So, we try to find the force at these locations for each flexure. So, the force at the tip of each flexure. So, F is calculated using this formula 3b over 4l into T1 plus T2 divided by 1 over T1 E1 plus 1 over T2 E2 into gamma 2 minus gamma 1 into delta T. Okay. So, if you plug in the values, we know the width of the flexure, length, thickness of both layers we know 2 micron, 10 micron, E1 and E2 we know. So, if you plug in, and we also know gamma 2, gamma 1 and delta T. Delta T is 400 degree. So, we can find 9.639 into 10 to the power minus 6 into delta T. Okay. So, delta T is 400 minus 25 degree C. So, now here we have to make an assumption. We can make an assumption that under evaporation, okay. So, we assume that when you do the evaporation of the aluminum layer, the 2 bonded metal layers are stress free. So, initially there is 0 stress acting. Okay. So, under evaporation, the bimetal is under 0 stress. So, in that case we can calculate F for a given delta T. So, F will be 9.639 into 10 to the minus 6 into 400 minus 25. So, that will be 3.615 into 10 to the minus 3 Newton. Okay. Now let us try to find the flexural rigidity of the composite beam. The flexural rigidity of the composite beam EI of the beam. So, we use the formula B1 E1 T1 square whole square plus B2 E2 T2 square whole square plus 2 B1 B2 E1 E2 T1 T2 into 2 T1 square T2 plus 2 T2 square divided by 12 T1 B1 E1 plus T2 B2 E2. So, using this formula we can find the flexural rigidity to be 3.774 into 10 to the power minus 9 Pascal meter 4. Okay. So, that is the flexural rigidity of the beam. Okay. Now, if you want to find the deflection of the beam, so deflection y will be governed by this equation. So, EI into dqi over dxq will be equal to minus f. Okay. So, this is the equation which will govern the deflection of the bimetal. Okay. So, what are the boundary conditions? To solve this equation, the boundary conditions will be the y dash, the slope at x equal to 0 is going to be 0. Okay. So, if you look at here, this is x equal to 0. Okay. That means at the base. Okay. So, the base, this is the flexure is mounted to a rigid base. Okay. So, the slope is going to vanish here, and also since the membrane is rigid, the slope will also vanish here. Okay. And also since it is rigid, the deflection will vanish here as well. So, y dash at x equal to 0 will be 0, and the y at x equal to 0 will be also 0, and the third condition is that the slope at x equal to L at the membrane, okay, will be 0, right. So, if you use these conditions, 3 boundary conditions to solve this differential equation, then you get the solution. So, by solving we get yx is going to be f divided by 2 EI of the beam into minus x cube by 3 plus L x square by 2. Okay. So, this is the solution for y. Okay. So, from there we can find what is going to be the maximum deflection. So, y maximum, so that will occur at x equal to L. So, that we can find as f L cube over 12 EI of the beam, which will be, so f we have found f equal to 3.615 into 10 to the minus 3. So, this is the force that we have found, into L is 5 into 10 to the minus 4 cube, okay, divided by 12 into EI. We have found the EI for the composite beam 3.774 into 10 to the minus 9. So, we can find the deflection to be 10 into 10 to the power minus 6 meter or 10 micron. Okay. So, we can allow a maximum gap of 10 micron, so that when the temperature is the room temperature at 25 degrees C, the valve will still be closed. Okay. So, there should be a 10 micron gap. So, gap between membrane and valve seat. Okay. So, with that discussion, let us move on and talk about the safe memory alloy based microvalve. The safe memory alloy is something, it can, if you apply a load, it will go through deformation, and it will remember its original configuration, and if we heat the metal or the alloy, it is going to come back to its original shape. That is known as safe memory alloy. So, we will look at safe memory alloy based microvalve, SMA stands for safe memory alloy. First, try to understand what safe memory alloys are. So, they are typically titanium nickel alloys, and they will change shape when deformed mechanically. Okay. But they will return to its original shape when heated. Okay. So, that is the property of the safe memory alloy, and the safe memory alloy will undergo a phase transformation upon heating. Okay. So, the SMAs will undergo phase transformation upon heating. Okay. So, normally at low temperature they will be in martensite form, and at high temperature they will become austenite. Okay. And this will have low Young's modulus, and this will have high Young's modulus. Okay. So, for that reason the safe recovery is possible when it is in martensite state. Okay. So, the safe recovery possible in martensite, but not possible in austenite. Okay. So, this is one such microvalve which is based on safe memory alloy. So, as you can see here, if there are here initially the valve is closed, okay, because that is the original state of the safe memory alloy, and when the pressure of the inlet fluid will increase, okay, when the inlet fluid here the pressure of it will be increased, then this metal this membrane holding the safe memory alloy is going to go up. Okay. So, the SEP memory alloy is going to go up. Now, when you want to again close the valve, then we supply heat. So, it is going to be heated. So, it will remember its original shape. Okay. So, its original shape will be remember, and so that the SEP memory alloy, when it tries to go to its original shape, the membrane is going to close down. Okay. So, this is what is going to happen. So, here we have SEP memory, the SMA will be in original shape. Okay. So, valve closed. Now, here in this case inlet pressure increases. So, valve open. Now, if we again want to close the valve, then we need heating of SEP memory alloy to bring it back to original shape. Okay. So, that is how SEP memory alloy based microvalves work. So, with that, let us move on to piezoelectric based microvalve. Piezoelectric based microvalve. Here we would have a piezo disc, as you can see here, and the piezoelectric materials are the materials which can undergo strain, or it can deform by applying an electric field. Okay. And they can be reversible, so that if you apply a strain, then it will produce charge. Okay. But in this case we are interested in deformation of the piezoelectric crystal. So, we will apply an electric field to create a deformation or deflection. So, when you apply an electric field, this piezo disc is going to deform, and that is how the valve is going to be actuated. Okay. So, let us try to understand what piezoelectric material is. So, typically they are the piezoelectric materials are PZT, which is lead, zirconate, titanate, or they can be PVDF. Okay, so, these are some of the examples of piezoelectric materials, which stands for polyvinyl, polyvinylidene fluoride, or they can be zinc oxide, okay, ZNO, zinc oxide. Okay. So, here we are interested in applying electric field and create deformation. Okay. And these piezoelectric materials have characteristic to produce small strain. They produce small strain, but high stresses. Okay. So, the strain is of the order of less than 0.1%, and the stress is of the order of millipascal. Okay. So, we would be using piezoelectric based micro actuation in microvalves, where we need small displacement, but large actuation force is required. Okay. So, the application would be where we need small strain but large, so small displacement but large actuation force. Okay. So, we can find out the strains this is the longitudinal strain, transverse strain, and so the longitudinal and transverse strains are going to be equal, which is D31 into electric field, and the vertical strain is going to be D33 into electric field. So, these are phi L, phi T and phi V are strains along longitudinal, transverse and vertical directions, and this is the electric field. Okay. So, now let us take a small example. So, here we are specifying a piezo bimorph. So, you have a piezoelectric material made out of two different metals, and the properties are given here. So, the dimension is 25 into 7.5 into 0.4 millimeter. We are applying plus minus 70 volts. This is the capacitance 20 nanofarad, and the maximum deflection is going to be plus minus 200 micron, and the force that we encounter is 0.5 Newton at a frequency of 300 hertz. Okay. So, the actuator is used for closing a silicon micro valve which has 300 into 300 micron valve seat. Okay. And and suspended on 4 flexures as described in the following figure. So, these the valve seat is suspended by 4 flexures. Okay. So, these are 4 flexures. The initial gap between the valve seat and the valve inlet is 20 micron. So, this is the initial gap that is shown here. The dimensions of the flexures are 500 micron, 100 micron and 20 micron. So, each flexure has this dimension, and the valve inlet is drilled in a glass substrate with a diameter of 200 micron. Okay. So, the valve inlet is sort of shown here. This has 200 micron diameter, 100 micron radius. We want to determine the maximum inlet pressure. Okay. So, this is how it is going to the characteristics is going to look like. At 0 deflection, the force is going to be maximum, and as the deflection occur, the force is going to reduce. Okay. And this is the spring force of the valve, and this is the force that is coming from the piezo bimorph. Okay. So, the spring constant for the valve seat, spring constant of the valve seat is modeled as 4 different beams. So, we can find the spring constant as 4 EW TQ divided by LQ. So, 4 into 170 into 10 to the power 9, and the width 10 to the power minus 4 into the thickness is 2 into 10 to the power minus 5 cube, okay, divided by 5 into 10 to the power minus 4 cube. okay. So this is 500 micron, right, L, it's 100 micron, this is 500 micron and this is 2 micron, right, sorry 20 micron, so 2 into 10 to the minus 5. So we get K as 4352 Newton per meter. So the characteristics are shown here as we described. So force and displacement of the piezo biomorph are inversely related and the wall spring will increase with deflection. So what we say, the maximum achievable force, the maximum achievable force at the displacement d0 is going to be, so F max at d0 is going to be F max into 1 minus d0 over y max, okay. So the d0 is the initial gap, right, so that is 0.15 into 1 minus 20 by 200, so that is going to be 0.135 Newton. So you can find the maximum closing force, the maximum closing force is F closing max is the F max at d0 minus the spring force. So which will be equal to 0.135 Newton minus K is 4352 into d0 is 20 into 10 to the minus 6, okay. So this is going to be 0.048 Newton. So that is going to be the maximum closing force, okay, whereas this is coming from the biomorph, okay. So this is coming from the biomorph. So we can find the maximum inlet pressure, maximum inlet pressure valve can withstand, valve can withstand delta P max is going to be F closing, the closing force max divided by the area, okay. So this is going to be 0.048 divided by pi into 10 to the power minus 4 square, that is the area, closing area. So it is going to be 15.28 into 10 to the power 5 Pascal, so which is about 15.28 bar. So we need we can maximum the force, the maximum pressure the valve can still be able to close is about 15.28 bar, okay. So with that let us stop here.